Welcome to the lecture on powder based processing. Melting parts, there are 4 common approaches for using powder bed fusion process in the creation of the complex metal component: fully melt, liquid phase sintering, indirect processing, pattern methods. So, full melting is you try to take 2 powders, you fully melt those powders. Liquid phase sintering is you have 2 powders where in between these powders on top you are coating with another metal which has a lower melting point, and this can give you a better consolidation. Then indirect processing and pattern methods we will see in detail. As discussed previously, in the full melting approach, a melting powder material is fully melt using high power laser or electron beam, and in liquid phase sintering approach, a mixture of 2 metal powders or metal alloy is used where a higher melting temperature constituent remains solid and the lower melting, that is what I said, lower melting constituent melts and it helps in sticking with each other. In indirect processing, a polymer coated metallic powder or a mixture of metallic and a polymer powder are used for part construction. So, once only for the part construction, after the part is constructed you burn the polymer. So, the figure in the next slide we will see shows the step involved in indirect processing of metal powder. During indirect processing, the polymer binder is melted and binds the particle together and the metal powder remains solid, that is indirect. The metallic powder particles remain largely unaffected by the heat of the laser. The parts produced are generally porous and the polymer bounded green parts are subsequently furnace processed. So, what you do is you try to get a shape out of the polymer binder, and you also heat the polymer binder so that these polymer binders can stick to each other and then form a shape. After it forms a shape, what is required? Then you take it to a furnace, blow or burn away all the binders. So, moment the binder is burnt, so what is left with you, you can take that and go for next stage of post heating process to get the required output. So, the metal parts furnace processing occurs in 2 stages, one is debinding and infiltration or by consolidation. During debinding, the polymer binder is vaporized to remove it from the green part. Typically, the temperature is also raised to the extent that a small degree of necking occurs between the metal particles. Subsequently, the remaining porosity is either filled by infiltration of a lower melting point metal to produce a fully dense metallic part, or by further sintering and densification to reduce the part porosity. This is very important. If you are happy with the porosity, live with it. If you are not happy, you try to infiltrate material. Where is the application? You make ceramic porous material and then inside the ceramic metal through the pores you try to infiltrate metals. So, these metals which are infiltrated gives you lubrication. Okay. So, there we use this application exhaustively. Infiltration is easier to control dimensionally as the overall shrinkage is much less than than during consolidation. However, infiltrated structures are always composite in nature, whereas consolidated structures can be made by a single material type. Infiltrated structures are always composite in nature. So, you will have a base structure. For example, what are we talking about? This is the base structure, and here are the infiltrated material. These are liquid infiltrates or solid infiltration. These are all the metal particles. Okay. However, the infiltration structure are always composite in nature, whereas consolidated structure can be made by a single material too. So, you make particles and then you bind it. After you bind, you try to sinter it and still you have pores, you infiltrate a liquid of the same material. The last approach to metal part creation using powder bed fusion method is the pattern approach. For the previous three approaches, metal powder is utilized in the powder bed process. But in this final approach, the part created in the powder bed process is a pattern used to create metal parts. Pattern used to create metal parts. The two most common ways of powder bed fusion created part are utilized as pattern for a metal part creation, or as investment casting patterns, or as sand casting patterns. So basically what we do is, in sand casting we try to make patterns. This is mold, this is sand, okay. This is a pattern which is created by this process. Investment casting also we can do. We can try to take this out of polymer, pattern out of polymer. Then what we do is we give a ceramic coating on top of it, heat the ceramic, so the polymer which is inside melts and dies off, or it is into liquid, you pour it off. Now what you have is a shell or ceramic shell. This ceramic shell can be used as a pattern, and then you can start making lot of applications. You can use polymer, you can use wax also. In the case of investment casting, polystyrene or wax based powders are used in the machine and subsequently invested in the ceramic during post processing and melted out during casting. In the case of sand casting mold, this is a sand casting mold, the mixture of the sand and the thermoset setting binder are directly processed in the machine to form a sand casting core, cavity or insert. Ceramic parts, like metal parts, ceramic parts also can be created. The only difference between metal and ceramic is metal lower melting point as compared to that of a ceramic. There are a number of ways that powder bed fusion processes are utilized to create ceramic parts. These include direct sintering, chemically induced sintering, indirect processing and pattern methods. Like in metals, here also you will have pattern methods. In direct sintering, a high temperature is maintained in the powder bed and the laser is utilized to accelerate sintering of the powder bed in the prescribed location to form each layer. The resultant ceramic part will be quite porous and thus are often post processed in the furnace to achieve higher density. This high porosity is also seen in chemically induced sintering of ceramics. The indirect processing of ceramic powder is identical to indirect processing of metal powder. What was the indirect way? This is what it is. So you will have a loose powder. So in the loose powder you can see metal or ceramic particles mixed with a polymer binder. These are polymer binders. So the powder bed fusion process happens. So this is consolidated and you try to make a green part. So you just melt the polymer. So the polymer stitches or ties the ceramic or the metal particle, and then what you do is you take it to a furnace, heat it. When you try to furnace heat it, all this polymer goes away and some amount of necking happens between the two particles, metal or ceramic, depending upon the temperature. And then what you do is you try to take it to further processing, furnace processing, you see a better consolidation happening. Okay. And here wherever there was a hole, vacant spot, you have infiltrated through some material. So that is as required. For example, copper can be done, aluminum can be done, lead can be done for your requirements for lubrication effect. Metals and ceramic particles binded with the polymer are seen here. Next, melting and resolidification of polymer binder enabling the complex part to be formed without thermally affecting the metal or the ceramic powder. So the particle is as such. Then the polymer vaporization and particle sintering at elevated temperature happens, resulting in a porous sintered component. Then you infiltrate with lower melting point metal, resulting in a density finishing component. So this is the flow for indirect processing of metals and ceramics. After debinding, the ceramic brown part is consolidated to reduce the porosity and is infiltrated. In the case of infiltration, this can be done by two: pressure, it can be done by positive pressure or it can be done by negative pressure. That is, vacuum can be applied, you suck and then allow the material to flow, or you pressurize the liquid material to flow. When metal powders are used as the infiltrant, then a ceramic metal composite structure can be formed. In such a case, such as when creating SiC structure, a polymer binder can be selected which leaves behind a significant amount of carbon residue within the brown part. Infiltration with molten silicon will result in the reaction between the molten silicon and the carbon to produce SiC. This is how people produce SiC parts, molten SiC and carbon, thus increasing the overall SiC content and reducing the fraction of Si in the final part. So, the variant of powder bed fusion processes, a large variant of powder bed fusion process have been developed today. What we have seen is only few successful processes, but people have come out with variants depending upon their requirements. To understand the practical difference between these processes, it is important to know how the powder delivery method, heating process, energy input type, atmospheric conditions, optics and other features vary with respect to one another. An overview of commercial process and a few notable systems under development are discussed in this section. Laser based system for low temperature processing. There are two major producers for low temperature laser bed powder bed fusion technique. These low temperature machines are designed for directly processing polymer and for indirectly processing of metals and ceramics. Both these companies sell and service their machines worldwide. Low temperature powder bed fusion machines designed for polymer processing are commonly called as selective laser sintering machines or laser sintering machines. The SLS machine model were commercially introduced, and these systems are currently manufactured and supplied by 3D System USA, which purchased DTM in 2001. This industry is fastly changing, and companies buy companies, companies sell companies. So, there is not a single owner for a long time. Like in automobile, we have few giants. So, in 3D, in rapid manufacturing or in rapid prototyping, we don't have a single giant. They buy, establish a technology, sell it, then establish another company. So, this keeps going. So, 3D System purchased DTM in 2001. So, this is the schematic diagram for laser sintering process, selective laser sintering process. So, you have a powder bed. So, in this bed you can have a polymer, metal or a ceramic. Powder can be there. So, this powder will be is there. So, this powder is now moved into a powder bed. So, this powder bed is otherwise called as a table. Thus, the powder bed moves up, the table moves down. So, the roller which rolls from one side to the other side tries to take the required quantity of a single layer of powder and spreads it on top of a table, and then this roller goes to the other extreme end. In the next time when the single layer information of sintering is over, the bed pulls it down by a single layer. This powder delivery piston goes up by a single layer. The roller takes the material from this extreme end and moves to the table and then goes to this extreme end. Okay. So, this extreme end. So, now what you have is layer by layer by layer information you have, and that is how it is done. So, here you have laser, this is the optics which is attached with the laser. This is the scanning mirror. So, it gives you 2D layer information for producing. The newer machines offer several improvements over previous machines in terms of part accuracy, temperature uniformity, built-in speed, repeatability, feature definition and surface finish. And by the way, you should also understand there is a heater placed around the powder bed. Here in the center portion there is a heating. It will not take you to very high temperatures, and then on the delivery piston here also you will maintain, or the entire system will be maintained at inside a small furnace at a lower temperature, not melting temperature, in order to make sure no contamination happens with respect to the free atmosphere. The water molecules should not be there and it should not react. So, they do it, or they put it inside a furnace and purge it with argon gas. So, the laser resolutions are improved, the powder size has been the powder size is been reduced, then uniformity in powder size is done, then the laser scanning speeds have become high, then the repeatability, the drive mechanisms have improved. So, these are certain things which are kept on going on in the SLS process. so that now you get better features. The 3D system low temperature machines are designed to run a large variety of powder material type. Due to the use of CO2 laser and nitrogen atmosphere with approximately 0.1 to 3% oxygen, these machines are incapable of directly processing pure metals and ceramics, and as such are optimized to process polymer materials, with nylon polyamide material being the most popular one. The other one is wherein which you use a binder which is kept in a printer head, and then this binder, instead of a laser, that laser is replaced by a binder head. This binder, the binder head or the next advanced version is removing the laser and then replacing with a print head. So, this print head will have a nozzle. This will be several nozzles, and through these nozzles, every nozzle you will have orifices. So, these are nozzle, these are orifice. Through this orifice, the binder material falls down, and this binder material drops on the location wherever you have to join the particles, and then you get an output. So, these are they can also process polystyrene based casting material and elastometric materials directly, and they often offer indirect processing of metal powders with polymer binders. This is an advanced next variant of SLS process. There are 4 big companies which make commercially available laser based systems for direct melting and sintering of metal and ceramic powders: ESO Germany, MTT UK, Concept Laser Germany, and Phoenix System France. So, all the four are a big player. Even now they are available in the market. They do a wonderful job, all the 4. They are competitive to each other. Not all of these companies sell and service machines worldwide. For instance, all 4 companies sell machines in Europe, whereas EOS and MTT actively sell systems in the United States. So, they also have a fixed market, they go through it. In India, you can get all the 4 through an agent, right. The most commonly used terminologies to describe this category of technology is selective laser melting. However, the term laser cusing and direct metal laser sintering are also used by certain manufacturers as mentioned in the following sections. For this discussion, we use SLM to refer to the technologies in general and not to any particular variant. Compared to polymers, the high temperature conductivity, the propensity to oxidize, high surface tension, low absorptivity of the metal powders make them significantly more difficult to process than polymers. These are important properties which have to be noted. Today, commercially available SLM, so the same laser cannot be used, the interaction time cannot be the same. Today, commercially available SLM systems are variant of the selective laser powder remelting approach developed by Fraunhofer Institute at Germany. Their research developed the basic processing technique necessary for successful laser based point-wise melting of the metal. The use of laser with wavelength better tuned to the absorptivity of the metal powder was one key for enhancing SLM process. For example, there is a red laser, green laser, blue laser. The response of the red laser, blue laser and green laser are completely different. So, depending upon the requirement, they choose the laser. Okay. And in terms of when you talk about laser material interaction, it is the absorptivity property which plays an important role. Subsequently, almost all SLM machines today have transitioned to fiber laser, which in general are cheaper to purchase and maintain, more compact, energy efficient and have better beam quality than Nd:YAG laser. 3D Micromac AG Germany is a laser processing company which has developed small scale SLM processors with small build cylinders of 25 millimeter and 50 millimeter in diameter and a height of 40 millimeter in height. So, today when we are looking at bio implants, when we are looking at microfluidic channels, when we are looking at electronics, when you are looking at MEMS application, where directly you want to produce from the start, from the building block, we use this technique for making the final part. In fact, there are certain complex geometries which are used, complex geometry parts which are used as ear implants, which is too difficult for you to generate through subtractive process, but the additive process develops it within no time. And again, you can also have functionally graded material there. So, this makes the implant very sensitive to even small deflections or change in pressure. So, for ear implants, SLM process is the only process used for making metal based parts for those applications. So, here it is rapid manufacturing, and as I told you earlier, when we try to do one layer, in a single layer you can initiate an array of metal parts together. So, maybe in one shot, like if you have 30 centimeter cross 30 centimeter table, and if your component size is hardly 2 centimeter, okay. So, now what will happen, you can make 25 or 30 parts, layer by layer by layer it can be done. When you finish one part, you will also get 30 parts. An array of parts are made. This is the new technology where people are using towards rapid manufacturing. You plan properly, use rapid prototyping techniques for manufacturing live applications. The fiber laser is focused to a particular small spot for small feature definitions. In order to use the fine powder particle size necessary for fine feature reproduction, they have developed a unique two material powder feeding mechanism. A build platform is located between the two powder feed cylinders. When the rotating rocker arm is above the powder feed cylinder, the powder is pushed into the feeder, thus charging the hopper. When the rocker arm is moved over top of the building platform, it deposits and smoothens the powder, moving away from the building cylinder prior to the laser processing. By altering between the feed cylinder, the material being processed can be changed in a layer by layer fashion, thus forming multi-layer structures. An exclusive distribution arrangement of ESO announced in 2005 may one day lead to machines becoming available to consumers who wish to purchase their own equipment. So, like desktop printing, we will have desktop 3D printing machines wherein which they can use laser, because the lasers are also becoming economical. Initially, which was a solid state laser, now it has become a fiber laser. Fiber laser are economical. Of course, when you go for higher powers, it has lot of other technical challenges, but nowadays the fiber lasers are becoming very economical. Replacing laser with electron beam is the new trend. Why? Because you want to have a precise control of sintering. So, electron beam melting has become a successful approach in powder bed fusion. In contrast to laser bed systems, electron beam uses a high energy electron beam to induce fusion between the metal powder particles. This process was developed in Chalmers University of Technology in Sweden. So, now today it is available in the market. Similar to SLM, the EBM process, a focused laser beam scans across a thin layer of pre-laid powder, causing localized melting and resolidification as per the slice cross section. So, it is a pixel of information, one spot. However, there are a number of differences between how SLM and EBM are typically practiced, which are summarized in the table. I will show you the table next. So, these are the summarizing thing: thermal source, electron beam, laser beam. Atmosphere, you have vacuum, you have inert gas. Scanning, it is a deflection coil. So, here we use, in EBM we use a deflection coil, here we use a galvo, because the galvo is used to give the information on XY plane. Then energy absorption is in conductive, here it is absorptivity. These two properties are completely different. This is a optic based property. Then preheating, use electron beam can be done, infrared can be used to avoid the contamination from the free atmosphere getting mixed. Scanning speed very fast, it is limited. Electron, because the laser can be, the coil is used, deflection coil is used, so it can scan at very high speeds. The energy cost is moderate, it is very high. Surface finish is moderate to poor, it is excellent to moderate. The feature resolution is moderate in electron beam, excellent in selective laser melting. Materials, it can be used for metals, it can be used for any metals and non-metals. This is a typical part, which is a knee joint which is made using H13 tool steel by using electron beam melting. You see a wonderful surface finish. Today, it has become a mandate and it has become an integral part of the knee surgery. See, the interesting part is when we start working on these knee joints, we realized many things. When I also worked, we realized many things. No two patients will have almost the same knee joint, because your body to mass index is different and your loading pattern is different on the knee. So, in that case, the knee joint is not constant for everybody. So, you have to first scan your knee, understand the negative counterpart. From the MRI information, try to make a polymer model, look at your knee joint. Once you have understood everything, then take the same CAD model, go to electron beam or use SLM process, try to make your part. So, this part is custom made for you. Many a times you can see that doctors are involved in doing a knee implant operation for 7 hours and 9 hours. The majority of the time is towards mass customization. How do we custom make this to the patient? The electron beam are inherently different from laser beam, as electron beam are made up of stream of electrons moving near the speed of light, whereas laser beam are made of photons moving at the speed of light. So, moving near the speed of light, here speed of light. When the electron beam is passing through a gas at atmospheric pressure, for instance, the electron interacts with the atom and gas and gets deflected. So, you need a vacuum chamber to be attached in the machine. In contrast, a laser beam can pass through a gas unaffected as long as the gas is transparent to the particular wavelength. Thus, electron beam is practiced in low partial vacuum environment, whereas the fiber laser is used in any atmosphere, provided the laser should be allowed to pass through. The electron powder bed are maintained at higher temperatures than SLM process. First, there are several reasons. The first is the higher energy input of the beam used in electron beam system naturally heats the surrounding loose powders to a higher temperature than the lower energy laser beam. Very important. So, that means to say you will have a spreading of a spot. In order to maintain a steady state uniform temperature throughout the build, the EBM process uses an electron beam to heat the metal substrate at the bottom of the built platform before laying the powder. It heats the electron beam metal substrate at the bottom of the built platform is heated before the powder is laid. By defocusing the electron beam and scanning it very rapidly over the entire surface of the substrate or the powder bed, the bed is preheated rapidly and uniformly to have a preset temperature. Suppose the temperature is too low, you apply so much of heat, conduction phenomena comes. Because of this conduction phenomena, there is the resolution is lost. As a result, the radiative and resistive heating present in most SLM system for powder bed heating are not typically used in EBM. It is not the resistive heating or infrared heating. By maintaining the powder bed at an elevated temperature, however, the resulting microstructure of a typical EBM part is significantly different from that of SLM. Completely different. If you see the microstructure, it will be completely different. E-beam gives a very good output. In particular, SLM, the individual laser scan line are typically easily distinguishable, whereas in individual scan lines are often indistinguishable in EB microstructuring. So, this is a very important advantage of using EB. You get a very smooth surface. The finishing, the post processing becomes very easy as far as electron beam is concerned. Rapid cooling in SLM creates small grain size and subsequent layer deposit only partially remelt the previously deposited layer. The powder bed is held at low enough temperature that elevated temperature grain growth does not erase the layering effect. In electron beam, the higher temperature of the powder bed and the larger and more diffused heat input results in continuous grain pattern resulting in contiguous grain pattern that is more representative of casting microstructure with little porosity than SLM process. Electron beam is very advanced and defect free because spot size, heating, controlled grain structure, you get the best output. line wise and layer wise powder bed process. The powder bed process have proven to be the most flexible general approach to rapid manufacturing. The large variety of the material, manufacture and applications that are available surpasses those of any other approach, powder bed. However, the use of expensive laser or electron beam, the fact that the beam can only process one point of the material at any instant of time, the overall cost of the system means that there is a considerable room of improvement. Why? Because the laser can go spot by spot, EBM also can go spot by spot. So now instead of going spot by spot, if I can put a small mask and allow light to fall, so the entire thing is done as one line in one shot with very high resolutions. As a result, number of organizations have developed ways to fuse lines or layers in a material at a time. So like photolithography. Photolithography is what? You have light, just take an X-ray. You have taken an X-ray, you fix the X-ray on a flat transparent tube light box, and the doctor looks at the X-ray. So it is almost the same. The tube light is coming from the other side, the X-ray is a mask which is put on the top, and the doctor is viewing from this side. So if the light is allowed to pass through the mask, and if that mask thus light tries to hit at the object, that is nothing but a powder bed. So then what you get is the entire layer information in one shot. You can do point, line, layer, or do line, layer, or do layer. All the three options are possible. If you do point, we use laser, we use binder, we use E-beam. When you use line, it is an exposure we can do in one shot. So you mix a polymer with a metal powder, and the polymer is cured by a UV light, possible. Okay. As a result, a number of organizations are developing ways to fuse lines and layers of material at time. Although these processes currently used to low of temperature to a process metal directly, the potential for polymer processing in a line wise or a layer wise manner could increase the build rate of powder bed process, thus making them more cost effective. So you see here, this is what is the example I gave, an infrared from the top, you have a mask, then you have a bed, this is a feeder cartridge, from the feeder cartridge this is a roller, this rolls and adds materials to the table, and the table sinks. So you get one layer of information, the mask layer is kept, IR is exposed, so you get one layer of information on the top. Three of these processes will be discussed below. All the three utilizes infrared to induce fusion in the powder bed. Heat. Basically, you can have metal and polymer also there, or you can use only polymer. The key difference lay in their approach to control which portion of the powder bed fuses and which remains unfused, as illustrated below. So you can use a mask type, you can use printing of an absorptivity enhanced agent in the part region, and then printing of sintering inhibitor outside the part region. So here it is inkjet. Okay, so here what is the inkjet printing of absorptivity enhancing agent. So here you just the jet is printed and then you use infrared. So this infrared is to create a layer. The third one is going to be inkjet printing of sintered inhabitants. So you have an infrared, you have a layer of information. So the center portion alone, the outside portion is done, center portion is not done. So the key characteristics of this technology are exposure of the entire layer at a time to infrared thermal energy through a mask and a rapid layer of powder making. Their powder delivery system can deposit a new layer in 3 seconds. The heat energy is provided by an infrared heater. A dynamic mask system, we can use DMD, or you can just keep flipping like a movie. Olden days you had a film roll passed through continuously and you see a movie. So in the same way, dynamic mask systems similar to those used in a photocopier to transfer ink to paper is used between the heater and the powder. This is a rebirth of an idea conceived by Cubital for layer wise photopolymerization in the early days. The SMS mask allows infrared energy to impinge on the powder bed in the region prescribed in the layer. The high speed sintering is process being developed at Loughborough University in UK. You see many of the variations are still in the research phase. The high speed sintering, an inkjet printer is used to deposit ink onto the powder bed, presenting a parts cross section of the layer. Ink are specially formulated to significantly enhance the infrared absorption compared with the surrounding layer. So, ink is spread, you have an infrared, so the ink cures, the powder joins, you get the part. The infrared heater is used to scan the entire powder bed quickly following the inkjetting. Thus, this process is an example of line-wise processing. The difference between the absorptivity of the unprinted area compared to the printed area means that the unprinted area do not absorb enough energy to sinter, whereas the powder where the printed ink is there, it absorbs. Again, as distinguishing factor between the fused and unfused region is the enhanced absorption of the energy. Where printing occurs, the ink are typically grey or black and thus affecting the color of the final part. The third approach, you just drop ink there and the ink is cured. Fine. The third approach to rapid powder bed fusion is the selective inhibition sintering process. In contrast to high speed sintering, the sintering inhibition is printed in a region where fusion is not desired, followed by the exposure of the infrared. In this case, the inhibitor interferes with diffusion and the surface properties to inhibit sintering. Yes, sintering, it is just a negative. A sintering inhibitor is printed in the region where fusion is not desirable. You put a negative to the previous process. In this case, the inhibitor interferences with diffusion and the surface properties to inhibit sintering. In addition, researchers have also utilized movable plates to mask portion of the powder bed where no sintering is required in order to minimize the amount of inhibition. The fused metal deposition system, a number of processes have been developed that uses the principle of blowing metal powder into the melt pool created by the laser. So, look at it. So, you will have a laser which comes and hits, then you have a powder metal supply with gaseous is done, and here is a plate to hold this gas feeding. So, the particle are hitting at the surface and the gas is used. So, this process is called as fused metal deposition process, or it is called as LENS, laser engineered net shaping. So, this was developed in Johns Hopkins University. So, here what happens, the laser moves, the plate where the two gases are there, that also moves. So, it is all coaxial, you get it, and then the carrier gas is also used to feed it. So, the process parameters are, as far as laser is concerned, laser power, spot diameter, pulse duration, frequency are very important. Scanning related properties are scanning speed, scanning space and scanning pattern is very important. Powder related, particle size, particle shape, distribution, powder bed density, layer thickness and material property. Temperature related parameters are powder bed temperature, powder feeder temperature and temperature uniformity. These are some of the process parameters which are very important to be controlled. To recapitulate, in this lecture what we covered was what are the approaches to metal and ceramic metal part creation, explain the different variants of powder bed fusion. So, we saw a spot, then we saw a line, then we saw a layer making. What are the different materials used for powder based fusion? These are certain things which we have gone through in this lecture. Thank you very much.